In a previous video, we learned about hashing. In another one, we learned about the sliding window technique. In this video, we will take advantage of both of them to make a string matching algorithm named the Rabin-Karp algorithm. Quick reminder of these three terms. Hashing is simply the process of converting a key to a fixed size value. For example, we may convert the key inside code to 48,635. How is it done? Why would we need it? All of these questions are answered in the video about hashing. Sliding window technique is a problem-solving technique that works by maintaining a window, a contiguous part of the data. Its advantage is that if we want to calculate something about the next window, we don't need to do it from scratch. We just take the value of the actual window and update it in some way, which is faster. Quick example, we have this window and we know that the sum of its elements is 25. If we want to get the sum of elements of the next window, we don't calculate the sum from scratch. We just take the sum of the actual window, add the new element, subtract the old element, and we got the new sum in O of 1 time. O of 1 because the length of the window doesn't affect the number of operations. Last term, string matching. String matching is the process of searching for the locations of one or multiple strings, also called patterns, inside a larger string. And there exist different string matching algorithms. We've seen one in this channel, the KMP algorithm. We're now ready to start. To search for a pattern in a string, there is a simple and straightforward way, the brute force algorithm. We have a string S of n characters and a string P of m characters. Two equal strings must have the same number of characters, m in this case because we're searching for P. So the idea is to compare all substrings of S of m characters with P. We start from the beginning. We compare the first m characters, they don't match. Then the next m characters don't match. Then the next m characters, they match, so we found P. We can continue like this to find all positions of P in S. You see, very simple solution. Why don't we just use it then? Why would we use a more complex algorithm that uses hashing and sliding window? It's because the brute force solution is slow. Yes, what we're doing is that for each index in S, except last ones, we're traversing the next m characters to compare them with P, which gives a solution of O of n times m time complexity. Quite slow. And this is why today we will learn about the Rabin-Karp algorithm. What's the idea of this algorithm? In the brute force solution, we have a loop that traverses indices of S, and at each iteration, we're comparing m characters, an operation that costs O of m time. And this is what we want to eliminate. We want to get rid of this part. How to do so? The idea is that instead of comparing strings themselves, we compare their hashes. In other words, by using hashing, we get the hash of each one of them, a fixed size integer, and we compare. The difference is that comparing integers is done in O of 1 time instead of O of m. But two problems arise from this reasoning. The first one is that calculating the hash of a string usually requires us to traverse the whole string, so it costs O of m in our case, which takes us back to our initial problem, having our iterations running in O of m time. And second problem, having two strings with the same hash doesn't necessarily mean that they're equal. Remember the concept of collision we talked about in the hashing video. It means that saying that we found P as soon as hashes match can be wrong. This is why, if hashes match, we double check by actually comparing the strings themselves before saying that we found P. I know, this looks like we went back to the brute force algorithm, but with a more complicated algorithm. But let's fix these problems. First, we said that calculating hashes takes O of m time because we need to traverse the whole string. Let's fix this. The pattern P doesn't change during the process, so we can calculate its hash once and store it in a variable. We don't need to do it at each iteration. And for substrings of S that we will traverse, windows, we will use the sliding window technique. We'll calculate the hash of the first m size window normally, then to get the hash of the next window, we just update the actual hash by taking into consideration the character that entered and the character that went out. So getting the hash of the next window now costs O of 1 only instead of O of m. We don't need to traverse all the m characters again, we just work with the new one and the old one. That was for the first problem. We still have the second problem, is that two keys with the same hash doesn't mean that they're equal, which requires us to double check by comparing the strings, which is in O of m time. Can we have a hashing function that gives a unique hash to each key? Because if it's the case, we don't need to double check anymore. This is what we want. Well, this concept exists, it's called perfect hashing, we talked about it before. But because we have a huge number of possible keys in our case, it's impractical. However, we can still use a hashing function that minimizes the number of collisions. We can use one that is good enough to say that if two strings have the same hash, we're almost sure that they're equal. The probability that they're equal is almost 100%. We still need to double check, but a good hash function will make us avoid a lot of unnecessary double checks. After introducing sliding window, here is our pseudocode. In the maximum ksum example we've seen in the sliding window video, we started by calculating the sum of the first window that consists of the first k elements. Then at each iteration, we update the sum by using the new element and the old one to get the sum of the next window. We will apply the same logic here. We start by calculating the hash of the first window that consists of the first m characters. Then at each iteration, after comparing, we update the hash by using the new character that enters the window and the one that goes out to get the hash of the next window. But what do we use as a hashing function? As you may know, we have a lot of hashing functions, but we don't use any one of them. First of all, we want a hash function that doesn't produce a lot of collisions, to avoid unnecessary double checking. And second condition, quite specific to our case, we want a rolling hash function, a hash function that is compatible with the sliding window technique. It means that if we have two windows like this and we have the hash of the first window, we want to be able to get the hash of the second window without traversing all characters again. We want to get it just by touching the new and the old characters, to get hashes of next windows in O of 1 time per iteration. Little recap before we dive into the hashing function we're gonna use. Brute force solution has an O of n times m time complexity because it traverses m characters at each iteration to compare. To improve it, we want to compare hashes instead of strings themselves, because comparing integers is an O of 1 time. But calculating the hash costs O of m, unless we use a sliding window technique with a rolling hash function to get the hash of the next window in O of 1. Also, two strings with the same hash doesn't mean that they're equal. This is why we double check by comparing strings themselves to be sure. Which takes time, but by using a good hash function, we reduce unnecessary double checking. So in brief, the Rabin-Karp algorithm optimizes the brute force algorithm by comparing hashes instead of strings, and also uses sliding window to quickly compute hashes. If you understood this, you're quite good. Even so, we still need to understand two important things: the hashing function we use and the time complexity of the Rabin-Karp algorithm. Let's start with the hashing function. Let's suppose that we want to hash a string p of m characters, like our pattern. For that, we need two other variables, d, the alphabet size, and q, a prime number to use modulo and avoid overflow. The alphabet size is the number of different characters our string can be made of. For example, if we're dealing with strings made of lowercase alphabetical letters only, the alphabet size will be 26. And the hashing function will be this one: the sum of the ASCII code of each character at index I multiplied by d power m minus I minus 1. All that modulo q. An example to understand. We have the string click of 5 characters, so m is 5. We also put d at 26 and q at, let's say, 101. It's a prime number. The hash of this string would be ASCII of c times d power 4 plus ASCII of l times d power 3 plus ASCII of I times d power 2 plus ASCII of c times d power 1 plus ASCII of k times d power 0, all that modulo 101, we get 43. So at the beginning, we calculate the hash of p and the hash of the first window. One small problem, however, is that because m and d can be quite big, calculating the sum can cause an overflow. To fix that and still get the same result, instead of calculating the hash of a key like this, by directly calculating the sum, we write this instead. We start at 0, then for each character at index I, hash becomes d times hash plus the ASCII code of the character, all that modulo q. You want the mathematical proof? Okay, fair enough. Let's stick to our 5 characters example. It's easier to understand than the general form. Actually, we're calculating the hash like this, right? Let's play around with this expression. You may know that d power k is equal to d times d power k minus 1. So we can factor by taking out d. Here we do it for the first 4 terms. We have d times p0 times d power 3 plus p1 times d power 2 plus p2 times d power 1 plus p1 times d power 0. By the way, d power 1 is d and d power 0 is 1. Now we factor the first 3 terms. We get d times p0 times d power 2 plus p1 times d power 1 plus p2 times d power 0. Now we factor the first 2 terms. We get d times power 0 plus p1. And we just put parentheses like this. Okay, now we got this expression. You need to know that a plus b modulo q is equal to a modulo q plus b modulo q. Also, d times a modulo q is equal to d times a modulo q. By combining these two laws, we get that d times a plus b modulo q is equal to d times a modulo q plus b all that modulo q. And we use this law to introduce modulo q like this, by considering d, a, and b like this. Same thing here, by considering d, a, and b like this, we can introduce modulo q. We do it again here, and we do it again here, we get this expression. Last thing, how to compute this expression. Remember that this expression represents the hash of p. We can do it like this, hash p starts at 0. Then, we multiply it by d, add p0, all that modulo q, we get a new value. Then again, we multiply it by d, add p1, all that modulo q. Again, we multiply by d, add p2, all that modulo q. And again, multiplied by d, add p3, all that modulo q. Again, multiply by d, add p4, all that modulo q. And we get the hash. And if you noticed, what we did here is that hash p started at 0, then for each character, hash p became d times hash p plus pi, all that modulo q. And this is why we could avoid overflow, by turning our sum into a sequence of safer operations. We can even define our hash function as a recursive function. Hashing characters of p until index I is equal to 0 if I is minus 1, it means we finished hashing. And d times hash of I minus 1 plus pi all that modulo q else. Okay, now we know how to hash while avoiding overflow. We use what we made now to hash p and the first m characters of s. In code, we will have 2 variables hash p and hash s. Then we traverse the m first characters of s and p while performing the operation we've seen now. Hash p becomes d times hash p plus ASCII of pi modulo q. Same logic for hash s. Next step, we can start traversing indices of s to compare and update. First, we compare. We compare the hash of our window, hash s, with the hash of our pattern, hash p. If they're equal, we double check by comparing strings themselves. We compare the next m characters of s starting from I with p. If they're equal, then we found p in s at the index I. That was for comparison, but what about updating hash s? We need to update hash s for the next window by removing the old character s of I and adding the new character s of I plus m. Yes, we can just calculate the hash again from scratch, but we don't want that. We want to go from the hash of the window I to the hash of the window I plus 1 in all of one time. Let's take this example and get ready for another mathematical demonstration. Here m is 5, so our first window consists of the first 5 characters of s. Let's calculate its hash. It's s0 times d power 4 plus s1 times d power 3 plus s2 times d power 2 plus s3 times d power 1 plus s4 times d power 0, all that modulo q. What about the hash of the next window, the one that starts at index 1? It's s1 times d power 4 plus s2 times d power 3 plus s3 times d power 2 plus s4 times d power 1 plus s5 times d power 0, all that modulo q. We want to go from this one to this one in all of one time. How to do so? First of all, we can notice that s0 times d power 4 is not present at all below. It's the character that went out. We want to remove it from the sum. But we don't remove it just like this. Notice that all this expression is modulo q. We have to respect modulo arithmetic laws. We have that a plus b modulo q minus a all that modulo q is equal to b modulo q. By putting a and b like this, a gets removed. A is s0 times d power 4. So by subtracting it and putting the result modulo q and using the law, we get b modulo q, where b is the sum but without the first term. Next step, we notice that powers have to be incremented to reach those in the expression below. For example, now we have s1 times d power 3, but in the final expression we have s1 times d power 4. To increment all powers, we multiply everything by d and apply this law. D times b modulo q is equal to d times b modulo q, where b is our actual expression. You can see that now powers match. Last difference, we don't have s5, we have to add it, it's the new character. We have this law, b modulo q plus c all modulo q is equal to b plus c modulo q. B is our actual expression and C is s5, the character we want to add. By applying this law, we can get everything as one sum modulo q, which is the hash of the next window as you can see. We've been able to get the hash of the next window by applying these 3 steps. Subtract s0 times d power 4 then putting modulo q, multiplying by d, and adding s5 then putting modulo q. Let's generalize. We have the window that starts at index I that consists of the next m characters, from index I to index I plus m minus 1 inclusive. So its hash is si times d power m minus 1 plus s of I plus 1 times d power m minus 2, and so on until s of I plus m minus 2 times d power 1 plus s of I plus m minus 1 times d power 0, all that modulo q. And we want the hash of the next window, the one that starts at index I plus 1. Its hash is s of I plus 1 times d power m minus 1 plus s of I plus 2 times d power m minus 2, and so on until s of I plus m minus 1 times d power 1 plus s of I plus m times d power 0 modulo q. For that, we subtract s of I times d power m minus 1 and set modulo q. We get this result. Then we multiply by d, we get this result. And then we add s of I plus m and set modulo q, we get the hash of the next window. We can even add modulo q for d power m minus 1 in the first step. In code, we add a variable h where we store d power m minus 1 modulo q to avoid computing it again at each iteration. And by the way, we should be careful when calculating it. D power m minus 1 can cause an overflow. And after comparing, we have to update. Note that we don't update in the last iteration because in the last iteration there is no iteration coming after it, so no need to update. We can't even update because there is no new character to add, so we add this condition. We must be before the last iteration. Inside, hash s becomes hash s minus ASCII of si times h, all that modulo q. Then we multiply hash s by d. And finally, hash s becomes hash s plus ASCII of s of I plus m, all that modulo q. And we get the hash of the next window by applying those three steps. We can even combine everything into one operation. Hash s becomes d times hash s minus ASCII of si times h plus ASCII of s of I plus m, all that modulo q. We can also store indexes where we find p instead of just printing, to be able to return them after as an array. And we got our Rabin-Karp algorithm implementation. I hope that math demonstrations wasn't too heavy. Let's apply it on this example and see if it really works. M is 4, D is 26, Q is 101, and H is d to the power m minus 1 modulo Q, which is 2. We calculate the hash of p. We start at 0 and apply the operation for each character, we get 34. Same thing for the first window of s, the first 4 characters, we get 47. Now we start iterations. First iteration, hash s and hash p don't match. We update for the next iteration, we get 13. Next iteration, they don't match. We update, we get 34. Next iteration, here they match. Let's double check. The window and p are equal, so we found p in s at index 2. Let's continue. We update, we get 80. Next iteration, no match, we update, we get 62. And it continues like this for remaining iterations. The result is that we can find p in s in 3 locations, at indexes 2, 8, and 11, which is true. Our algorithm worked. Last thing to talk about, time complexity. Because after we did all of this, we obviously ask ourselves if we got an improvement. This is what we will see. First, we have a loop that traverses m characters while doing O of 1 operations. Then we have a loop that traverses n minus m plus 1 indexes. All operations are in O of 1 except comparing the strings, which costs m. However, this operation doesn't always happen. It happens only when hashes match. And hashes match in 2 cases, when we find p and when there is a collision. In the worst case, c can be equal to n minus m plus 1. Hashes match at each iteration. For example, when we have a very bad hashing function or p appears at each index, we get an O of n times m time complexity. But with a good hash function, most of the time we'll probably have no or very few collisions. Same thing for appearances. The number of appearances is usually way smaller than n, if not 0. So we can say that in the average case, Rabin-Karp algorithm has an O of n plus m time complexity, way better than O of n times m. But we still have O of n times m time in the worst case. We've come to the end of this video. I hope that you understood how does the Rabin-Karp algorithm work. If you enjoyed, like and subscribe to the channel, or you can buy one of the Inside Code courses that you can find below in the description. See you in the next video.